Hello students, I'm Rahul Sharma and this is episode 2 on divisibility rule in the decimal system. In episode 1, we had briefly discussed about the Ioqm, which is the Indian Olympiad qualifier in mathematics, the first stage where students from 8th to 12th standard can appear for one exam, which is of 3 hours duration. And this exam takes place in the month of October, November, and those who clear Ioqm, around 500, 600 students in number all across India, they can get a chance to have a crack at Indian National Maths Olympiad, our exam held in the month of January, February every year. In episode 1, we had covered divisibility rules in decimal system, which is base 10 for 2, 5, 3, 9, 11, and composite numbers. We are continuing from episode 1 now and we'll cover prime and odd numbers divisibility rule other than multiples of 5. And I have been promising that we'll discover a law rule that holds true for all odd numbers, be it composite or prime. And that would help to derive the divisibility rules on the fly. One doesn't need to remember these. There is a new concept of seed that we are introducing now, and every odd number, including primes and composite, they have a seed. Now, what's a seed? You can say the seed is a number on which you can apply the divisibility rule for any odd number. And how does this work? Say if you have an n-digit number, let's say you have a 3-digit number, then the last digit will be multiplied by the seed number for that particular number and added to the rest n minus 1 digit numbers. We'll go slow here and try to understand. For the time being, let's assume, and we will prove it in subsequent slides, the seed of 3 is 1, seed of 7 is 5, seed of 11 is minus 1, and seed of 13 is 4. So what does it mean? Let's say you have a 3-digit number, which is 231. Now, what we are saying here is the seed of 3 is 1. So the last digit of 231 will be multiplied by 1 and added to rest of the number. So in case of 231, the last digit 1 will be multiplied by 1 and it will be added back to 23. That will give us 24. It suffices to arrive at a 2-digit number to check for divisibility, but you can go next step also. At times what happens is when you get a 2-digit number, the next step applied actually yields a number which is higher than the 2-digit number in the previous step. But let's take another step here. For 24, multiply the last digit 4 by 1 and add it with the balance number 2. It becomes 6. 6 is divisible by 3. Hence, 231 will be divisible by 3. Let's check for the same number for divisibility by 7. We are claiming that the seed of 7 is 5. So what do we do here? The last digit 1 will be multiplied by 5 and added to 23. That number becomes 28. 28 is divisible by 7. Hence, 231 becomes divisible by 7. Let's take the case of 11. The seed is minus 1. So 1, the last digit gets multiplied by minus 1 and it gets added to 23, which yields 22. Hence, this is divisible by 11. The seed of 13 is 4. So multiply the last digit 1 with 4 and add it to 23. The answer comes 27, which is not divisible by 13. However, if instead of 231, the number was 221. If this was 22 plus 4, 26, 221 would have become divisible by 13. Now we have to remember the seed of an odd number or a prime number can be multiple. What we are interested is in deriving the minimum seed, which is also called the root seed. So when we say the seed of a prime or odd can be multiple, that means take example of 3. 1 is the seed. You add to 1 any multiple of 3. 1 plus 3 becomes 4. So 4 also acts as a seed. So 23 plus 1 into 4, that becomes 27. That will also be a seed. In case of 7, again, there can be multiple seeds. 5 is the seed. Hence, if you add any multiple of 7 to 5, that also becomes a seed. 12 is also a seed. 19 is also a seed. minus 2, because 5 minus 7 is minus 2, it's also a seed, and minus 9 is also a seed. So in some of the textbooks, you may have been reading that the other way of checking for divisibility by 7 is you multiply the last digit by 2 and subtract for rest of the numbers. In case of 231, we multiply 1 by minus 2, which is also a seed, and we add balance rest of the number. It becomes 21. 21 is divisible by 7, and hence 231 is also divisible by 7. A prime can have multiple seeds. However, we are repeating here, we are interested in finding the smallest or the root seed, as that would help us solve the problems in an efficient manner. Let's take another example to reinforce the concept of seed. Let's say our number is 1638. So we are checking for divisibility by 3, and we have said that the seed of 3 is 1. So what we'll do here, we'll multiply the last digit with 1 and add to the rest of the number. So the first step becomes 163 plus 8 into 1, which is 171. We reapply this rule to 171, and it becomes 17 plus 1 into 1, which is 18. 18 is divisible by 3, hence 1638 is divisible by 3. Let's check for 7. The first step is to multiply the seed of 7 with the last digit, which is 8 into 5, and add to the rest of the numbers. So it becomes 163 plus 8 into 5, which is 203. Reapply this step again. It becomes 20 plus the last digit of 203 is 3. 3 into 5, which is the seed of 7. So it becomes 35. 35 is divisible by 7. Hence, 1638 also becomes divisible by 7. The seed of 3 is 1, which is same as saying that for the number to be divisible by 3, the sum of the digits also need to be divisible by 3. In fact, in episode 1, we understood for divisibility criteria by 3 and 9, the sum of the digits have to be divisible by either 3 or 9 for the number to be divisible by 3 or 9. And by saying seed of 3 is 1, and also subsequently we'll discover the seed of 9 is also 1, it is the same thing as saying the sum of the digits have to be divisible by 3 or 9. We'll see it why. Let your n digit number be a1, a2, a3 till an, where a1 is not equal to 0. So when we say seed of 3 is 1, the first step we'll be checking is, we'll be multiplying the last digit with 1 and adding with rest of the numbers. So the first step becomes a1, a2 till an minus 1, the first n minus 1 digits plus a into an. We reapply this in the next step. It becomes a1, a2 till the first n minus 2 digits. The last digit gets multiplied by 1, and in the first step, we had 1 into an. So in this step, the seed number will again get multiplied by that expression. So it becomes 1 into an. In the next step, it becomes a1, a2 till an minus 3 plus 1 into an minus 2 plus seed numbers multiplied by twice. So it becomes s square into an minus 1 plus seed numbers multiplied 3 times plus an1. Since the seed of 3 is 1, all powers of 1 will yield 1. So eventually at the end, we'll be left with a1 plus a2 till an. And that's what we are saying. If the sum of the digits is divisible by 3, then the number will also be divisible by 3. Now let's understand what exactly is the seed of a prime p and why does it work. So seed of a prime p is a number s such that p divides 10s minus 1. Let me actually highlight this. I'll repeat it. The seed of a prime p is a number s such that p divides 10s minus 1. This expression, it stands for p divides 10s minus 1. In case of 3, when p is 3, we are saying p has to divide 10s minus 1. What can be the minimum s? S will be 1. Then only 3 will divide 9. And hence seed of 3 becomes 1. In case of 7, when our p is 7, we know 7 into 7 is 49. So we have to, it basically becomes 50 minus 1. 7 divides 50 minus 1, and hence s becomes 5. The seed becomes 5. In case of 13, we know 13 divides 39, which is 40 minus 1. So hence seed becomes 4 of 13. Now, why does this work? Let's say you have a n digit number. It can be written as form of 10a plus b, where a are the first n minus 1 digits of that number. After applying the seed to this number, you get a new number, which is a plus s times into b, right? And we have spoken about the seed of a prime other than multiples of 2 and 5. So for the number to be divisible by n, n minus 10 has to be divisible by p. This implies 10s minus 1 has to be divisible by p. I hope students can see this. In fact, what we discussed previously, that a prime p can have multiple seeds, holds true, because s can also take multiple values. For 3, s can take a value of 4 also, because 3 divides 39. S can take a value of minus 2 also, because 3 divides minus 21. What we are interested is in to get the minimum absolute value of that prime number. In case of 11, we know 11 divides 99. 99 is 100 minus 1. That becomes, so s becomes 10 for us, which is also same as saying if 10 is the seed of 11, then 10 minus 11, which is minus 1, is also the seed of 11. In the previous slide, we discussed when seed was 1, the sum of the digits was working as a divisibility criteria for 3 and 9. Now for 11, the seed is minus 1. So can you see why this alternating plus minus, where we see add the odd number of digits and subtract from even number of digits, will work for 11? Let it be a small exercise for you. If you have still not figured out, please let me know and we'll work it together to have this figured out. But I'm sure most of you will be able to do on your own. Let's derive the seed of primes other than 3, 7, 11, 13, which we talked about just now. So seed is a number such that p divides 10s minus 1. In case of 17, we know 17 into 7 is 119. So 17 divides 120 minus 1. Hence, our s becomes 12. In case of 19, it divides 20 minus 1. Hence, seed becomes 2. In case of 23, it divides 70 minus 1, 69. Hence, seed becomes 7. Let's take case of 29. 29 divides 29 minus 1. Hence, seed becomes 3. Check for yourself. The seed of 31 is minus 3. The seed of 37 is minus 11. We are interested in getting the minimum seed, which is a minimum absolute value. Let's check for another number to see how this divisibility rules are working. Let the number be 10,013. So first we check for divisibility by 17. The seed of 17 is minus 5. Multiply the last digit with minus 5 and add it to the rest of the digits, 1001. This becomes 986. Reapply this step, multiply the last digit with minus 5 and add it to the rest of the digit. It becomes 68. 17 into 4 is 68. Hence, 10,013 is divisible by 17. Check for 19. The seed of 19 is 2. Multiply the last digit 3 by 2 and add it to rest of the digit. It becomes 1007. Reapply this logic, multiply the last digit with 2, add it to 100, this becomes 114. Reapply, it becomes 19. Hence, this number is also divisible by 19. In the case of 31, the seed is 28 or minus 3. When you do computation, multiplying the digits with 28 adding, it becomes a bit cumbersome. So take the number with minimum absolute value, which is minus 3. Do the steps and you will realize 10,013 is also divisible by 31. So far we have been talking about p as prime only, but it is easy to see p does not necessarily need to be prime. It can be any odd number other than the multiple of 5. And the same logic applies, which is p has to divide 10s minus 1. So in case of 9, 9 divides 9. So our s seed becomes 1. In case of 21, the seed becomes minus 2 because minus 20 minus 1 is minus 21. 21 divides minus 21. In case of 27, the seed is minus 8. In case of 33, the seed is 10 because 33 divides 100 minus 1, 99. And in case of 39, the seed becomes 4. Now let's trace a step back because we discussed about the divisibility criteria by composites. And we had said that break the composite into two numbers such that their GCD is 1 and check for the individual numbers respectively. So in case of 21, it can be written as 3 into 7. GCD of 3 and 7 is 1. And hence we just have to check for the divisibility by 3 and 7. And seed of 21 is -2. You'll agree on this? But I mean, why is it that it's not matching with our earlier concept? It is actually matching with our earlier concept also. Because we know seed of 3 is, what is the seed of 3? Seed of 3 is 1. The seed of 3 is also -2. Because we said you add or subtract any multiple of the number with the root seed and that becomes your seed. We discussed the seed of 7 is 5. The seed of 7 is also -2. So this thing is matching. The seed of both 3 and 7 is -2. Hence the seed of 21 is also -2. And we see the seed or the root seed of the numbers does not necessarily need to be unique. Let's take the example of 39. 39 is 3 into 13. The seed of 39 is 4. Now what's the seed of 3? Here we talked about seed of 3 is 1 and -2. Seed of big 3 is also 4 because you add 3 to the root seed 1. The seed of 13 we have already discussed is 4. All right. So the seed of 39 is also 4. So to check for divisibility by 39, we are already checking it by divisibility by 3 and by 13. So it is automatically fitting into our concept. Now let's summarize these rules because we discussed 5 rules. And these 5 can further be broken into just 2 rules. The rule number 1 is for the power p of 2 and 5. The rule is check for the last p digits only. If the last p digits are divisible by power p of 2 or 5, then the number will be divisible by power p of 2 and 5. The next rule is to check for any odd number which is not multiple of 5. Derive the seed. How do you derive the seed? That odd number has to divide 10s minus 1. And whatever is your s, it becomes a seed. And what do you do with seed? You multiply the last digit of a number with seed, add to the balance rest of the number, and keep repeating this process. So with this just 2 rules, you're done with your divisibility criteria in decimal system. Say you have the n digit number a1, a2 till an, where a1 is not equal to 0. So n is divisible by odd p if and only if. I hope all of you understand this IFF. It works both ways. If and only if. For the seed s of p, this expression holds true, which is a1 plus s times, where s is the seed of that odd number, into a2 plus s square into a3 all the way till s to the power n minus 1 into an if it is divisible by p. And it is easy to see this expression is nothing but we are reapplying the seed rule. We first applied the seed s to the last digit an. In the next step, we again reapplied the seed s. So we kept on applying the seed n minus 1 number of times. And when you do that, you are left with this expression. This is a very useful expression and it helps us solve a lot many problems when it comes to divisibility criteria by odd numbers or primes. So if you have reached this slide, then thank you very much. I hope we were able to discover some of the things on divisibility, and it's very conceptual. At least when somebody asks me these questions like the rule on divisibility rule on 7, 11, 13, 17, 29, I remember none of these. I just used that 10s minus 1 thing, and on the fly, the rule gets generated. So while theory we have understood, in the next session, it makes sense if we solve some problems. And some of these are tournament problems. I have listed some 3 problems. The first problem is broken into 2 parts. These are slightly your appetizers to start with. The second problem is Ioqm level problem. In Ioqm, typically you have questions of 2 marks, 3 marks, and 5 marks. It depends on the mood of the person who has set the paper. But the second question will be for 3 or 5 marks only. And then lastly, we'll also look at the Indian National Maths Olympiad question on the same theme, which appeared in 2003. Thank you, students, for your patience. Keep smiling and may the force be with you.